All right, I think we should be live. Um, okay, so today, I think the thumbnail on this video is wrong. If you're watching the live stream, this is probably showing the wrong thumbnail. But anyway, if you made it here, thank you. It's going to be a cool one anyway, even if it isn't what the thumbnail says. If you're watching this in the future, probably the thumbnail will be fixed. But hello, everyone. Today, I'm back. After a couple of weeks of no videos, no stream, but I think I've got something pretty cool for you. Today we're going to be going back into sort of supercharging Node with hardware capabilities mode. And we did this a little while back. I think we started this even a couple of months ago now with the Bus Pirate. And I made a whole series of videos with the Bus Pirate which basically went through the process of kind of building a low-level driver for that. So communicating with over some sort of binary protocol over a serial terminal to the Bus Pirate device itself in order to basically enable us to speak to that hardware. And then once we had that, the Bus Pirate is actually a sort of USB Swiss Army knife. It allows you to plug in different kinds of other hardware into the Bus Pirate, and then sort of we go as a proxy through the Bus Pirate to talk to this other hardware. Yeah, and today we're going to be looking at another device from FTDI. It's actually just a chip this time, so it's not a whole device like last time. The Bus Pirate is a whole board with multiple chips on it and kind of a whole firmware stack on board and a sort of software interface on this side. In this case, we're just talking to a chip directly, and it's a chip from FTDI. It's called the FT232H. Don't worry too much about model numbers and that kind of stuff because that's not that important for now. But yeah, and so this is just some of the things we're going to be going through today. We're going to be looking at the difference between these two devices. We're going to be looking at kind of an overview of serial protocols in general, because that's kind of something that this chip is is really, really good at, is able to do serial protocols, but not specific ones in a kind of abstract sense. We're going to be looking through some early code for how this works with Node, and then what we're really going to be looking at is the code that really makes this thing work. So this, unfortunately, fortunately, unfortunately, it's not really a value judgment in this case, but the FT232H doesn't speak, just a serial protocol like the Bus Pirate did, so it's not as easy to get going with it. In fact, the route that I've gone down in order to talk to this piece of hardware is to write a native Node add-on in C++ in order to kind of facilitate the communication there. And so we're going to be looking into that code and how that works and how Node add-ons kind of work in general. And I think it's going to be a pretty interesting one. There's going to be a lot of stuff here that I know for sure is not covered very well on the internet so far, because I've been looking for it. So I know that there isn't a whole lot of good information about kind of how to get going in this stuff. But I'm going to show you what I've got so far. So let's actually go over and take a look, kind of do a comparison between the Bus Pirate and the FT232H. So starting out with the Bus Pirate, this is this board that we've been working with a whole bunch in the last videos. I've got one here as well. The one you see on screen is a slightly earlier model, but it doesn't make any difference. The hardware setup is pretty much the same. So the way this thing works, this is kind of the pipeline, if you will, like the kind of data pipeline. So what we have is commands coming in through USB, and that comes over a serial port. So we're actually talking to a kind of virtual serial port with a USB driver specifically for that. And those commands, they come in and they end up in this chip here. And this chip is something called an FT232RL, And you'll notice that that's a very similar model number to the one that I was talking about earlier, which is an FT232H, or HQ in this case. And that is because they're made by the same manufacturer. And not only that, they are in the same kind of family, if you will. So they come from the same sort of philosophy of chips, but the one we're going to be looking at today is way, way more advanced than the one that's on this board, and that's kind of, in a way, what gives it its superpowers. Hey, I see some people in the chat there. No view, black screen. Well, I can see a view of the stream myself, so it looks like it should be working. Hey Nate, how are you doing? Alright, so this chip here, this FT232RL, that is kind of what allows this device to talk to the USB port. This chip is kind of a USB serial adapter, and it's everywhere. You'll find it on, like, if you open up devices that have USB ports and that do kind of, basic, simple things, tons of them will just have this chip inside, because they're super cheap and they're really easy to interface with, and they give your hardware are also a really simple interface. So it means that the if you're the embedded person building firmware for this device or any device, it means that you don't have to do anything too complicated to get those commands into your system. You don't have to have any really advanced stuff. It's kind of everything you need is probably already going to be there. So that turns into what we know as what we would call TX and RX signals, so transmit and receive. They're just a really simple protocol, and if you've used Arduino and that kind of stuff, then you'll be familiar with it, right? It's the serial port, it's the thing that allows you to print out to the computer, and incidentally, a lot of Arduinos have this exact chip on them. Okay, so the data comes in here, and then it's kind of translated into these TX and RX signals. And then it goes into this next chip. And this next chip's actually a little microprocessor, right? Not a microprocessor, a microcontroller. I think I've used the word microprocessor in a couple of places, but it's a microcontroller. So it's a PIC chip, it's a 24F, and what that does, well, that has basically a whole software stack inside that's able to take these commands and use all the hardware that it has internally to talk to the outside world. So what that is actually doing is taking the commands we put in and saying, oh, you're asking me to speak SPI, you're asking me to send this data, all right, I'm going to do that, and then it kind of sends out over these chips, these pins here. That's your output. And this chip down here does some stuff to do with like turning pins on and off. It's not too important for this part. So I want to contrast that with the FT232H Q. There are different model numbers for that, but this is actually, it's only this chip here, right? So it's only this little chip in the middle, and what you're seeing here around is a breakout board. So this is a board made by Adafruit. It's the one that I happen to have here. It's there are other ones around, but this one's really readily available, super easy to get a hold of. And it's got a nice interface, and it's kind of got all of this surrounding stuff. So, if you don't want to design this yourself, especially, it's got all of these passive components. It's got a little piece of memory on there that can store some stuff to tell the chip when it boots up. So it kind of takes care of a lot of that for you. And so the data flow for this one is way simpler. So what happens is the commands come in. They're still kind of commands, but they're different commands, of course. So commands come in, and they're not coming in by serial this time. This time they're coming in by native high-speed USB. So this is just pure USB data streaming into this thing. No serial port overhead, and serial ports are really slow. So in terms of this kind of data exchange, serial ports are super slow, and native high-speed USB is really, really fast comparatively. And so already off the bat, like, that's one huge advantage, right? This chip is way, 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 way faster than the bus bar. And kind of what comes in is the commands come in, they go into this this chip, which is not a microcontroller or a microprocessor, right? But it's not a CPU of any kind. It's a dedicated piece of hardware, right? It's got something inside it called an MPSSE, which is a multi-protocol synchronous serial engine. And that's a special piece of hardware that is built to take in commands, kind of like instructions for a CPU, but kind of different as well. It takes in these commands, interprets them, and then kind of pushes out or pulls in data across these pins. So the multi-protocol data, basically, our commands come in and the data streams out across these pins. And I've labeled these ones because this is what you use most of the time, but also you have access to those pins up there as well. So that's kind of a really, really, really quick overview. Just going to take a look at the chat. So Caribou says, I mean, Arduino USB serial interfacing with Node, but it's like pure black magic. Yeah, so the serial port, if you use it with Node, typically there's a library already, Node serial port, and it takes care of like all the nitty-gritty details of the serial protocol. But yeah, I mean, in essence, if you watch some of Ben Eater's videos, there are some good stuff out there. He really explains it in detail. Electrically, it's also just, pulsing some bits up and down, and there's some complicated stuff that goes on with the fact that it's one line and the line kind of times itself, so there's no clock signal that goes along with it. It's embedded in the data. But aside from that, I mean, you're just really sending bits down the line. It's electrically one of the simpler ones out there. So this is already a simpler data flow, right? I mean, of course, we've just put commands here. So commands, that means different things. And maybe the commands are really complicated. And some of them are, you have to learn this command set. But once you know it, that's pretty much how it goes. And I mentioned this MPSSE thing. And that's what's really like the coolest thing inside this chip. What that is basically an abstraction of all serial protocols into kind of their essence, so that instead of telling this chip, hey, I'm sending you some data and I want you to speak SPI across like 4 of your pins, instead what you're doing is you're kind of describing the essence of SPI itself, and then saying, okay, when I give you data, kind of do it in that essence that I described to you. And so in that way, you're not directly hooked into any implementation or any specific thing about like SPI or I2C or something like that. You can actually go off the beaten track a bit and you can do something outside of it. And sometimes that's necessary, right? Some proprietary hardware out there will have like something that's basically SPI, but then there'll be something like one weird little thing that's different about it, and that means that all of your normal hardware that can do that just won't be able to speak to it. But something like this can actually do it because it's not speaking SPI directly or any of these serial protocols. It can actually natively do serial port, but that's something different. I see Greg has entered the chat. Hey Francis, really excited for that today's streams. Native modules for Node have always been an interesting thing for me. Yeah, cool. I'm really, welcome. And I'm really glad as well because I also didn't have a whole lot of experience with them before. And in the last, just the last week or so, I haven't really put a ton of time into it, but in a few hours, I was able to get something up and running, and I was surprised at kind of how accessible it is once you're able to dig the information out. And that's kind of the hard part that I went through, is kind of finding the information. I don't think there is a whole lot of good resources out there. I think most of the time what you have to do is read other people's code, which is a fine way of doing it, but I think it can be intimidating for a lot of people Also myself, often I'm like, wow, I have to dive into a whole project in order to figure out how to do the basics of this one thing. But it's not too bad. So, all right. So, just a little quick diversion into serial protocols in general, because that's kind of what the MPSSE is doing for us. So serial protocols, they're all kind of the same in a lot of ways, right? Typically what you have is two electrical lines, and they might have specific characteristics, like I2C has some specific characteristics electrically that it requires. SPI has kind of more relaxed constraints in that way, and it has more electrical lines. But mostly what's happening is you have one of those lines is a clock signal, so that just pulses up and down and up and down. And the data that you send is on another line, and it's in time somehow with the clock. So it might be that when the clock goes to the high position, like some short amount of time later, the data is like should be sampled. It might be that when the clock goes low, that's when data should be sampled. It might be some kind of combination or variation on those two. So this is kind of an example of that. So this is a clock signal, this is a data signal. And in this kind of imaginary serial protocol, I mean, it's not anything too special here, but in this imaginary serial protocol, we say that the data is kind of valid on the falling edge of the clock. So when the receiver is kind of getting this data, it's watching this clock signal. And when it sees it go down, it says, okay, that's when I'm going to grab the data. I'm going to sample it here. So in this case, what happens is, and usually in these protocols, like the clock isn't running all the time either, because you're not always sending data. And so in order to mark when transactions are going to happen, the clock is usually in some kind of idle state. And then there's some transition to like a high, and then that's like, oh, there's a transmit coming, I need to listen. So that's kind of the imaginary indicator we could give here. So the clock is in its idle state, it goes up to high, and it's like, okay, high to low marks the start, this is where data is coming, so whoever's receiving this is like, they're now listening, they're waiting for this falling edge. So the falling edge comes, and the data is sampled, and in this case, it was a 0. And so, okay, there's another high, and then another low, and in this low, at that time, there was a 1 on the line. Again, we go through, there was a 1 on the line, get to this falling edge, there's a 0 on the line, and this one over here, and there's a 1. And typically we're going to send like 8 bits probably, or some more, or some, typically we're going to send bytes at a time, but, that changes as well. But we're just sending bits out, and eventually we go back to some indication of the kind of idle state, which might just be we turn the clock off, and then we just keep the line low. So kind of something to note here is that, of course, we could clock the data on the high end. We could clock the data kind of in the middle of the clock period. Presumably, both devices understand that they should be running at a particular rate, but rates can be variable and that kind of thing. When I say rate, I mean like how often this changes from high to low, the frequency. But in general, this is kind of it, right? And you might add more data lines here to kind of push more parallel stuff through. In SPI, for instance, you have 2 data lines, and one is an input and one's an output. So you're sending and receiving at the same time. But you can imagine you might also have just like, 3 or 2 data lines, and then you can send 2 bits at a time, right? It's a little bit faster in these serial low-speed protocols. So that's kind of something in general. Another thing that's really, really important to notice is that the clock here is drawn as this perfect square wave. I mean, obviously in reality that's not true, like there are no perfect square waves or anything like that. But you'll see here that the data is kind of drawn as a little bit like it has transitions, right? It's very clear that the data just doesn't start at one point and stop at another point. There's like this transitionary time where it takes time to stabilize. And you can imagine, right, if we were going to sample and we ended up sampling like somewhere in the middle here, we're going to be uncertain about which value we get. It's not going to be, it's like everything goes out the window. We don't know if it's going to be a 1 or a 0 at this point. And same here, right? It could be a 1 or a 0. When we're changing, it's not really clear. And so this is kind of the essence, right? There's this idea of the clock, there's the data, and there is this idea that also like time is a factor, so the amount of time it takes to go from like one piece of data to the next. And all of that obviously has to fit within a clock period, but there are some constraints around that as well. And all of this essence, that is what the MPSSE is doing. That's what this special engine hardware that runs inside the FTDI chip, that's what this takes care of. And we just describe the parameters of like how that kind of construction works, where the data is valid, when the clock is coming up, like when the data is clocked out in reference to the clock, all that kind of stuff. That's what the engine takes care of. So I hope that's in some way clear. You don't really need to know kind of all the details of this to go forward, but it's good to kind of have this in your mind as to why some of the commands might be like that when we eventually start talking to the FTDI chip. All right. I have no idea about this video, but it's magic. I leave like, and I'm leaving because I feel overwhelmed. Great work. I will return when I have experience. I hope to see you again in the future. It's one of the things that I try to tell people every now and again is that if you're watching something or reading something, or you're if you feel like you're watching something and you're like, I get like only 20, 30, 40% of what's going on and the rest is going over my head, I think that is one of the best places you can be. And I'm not saying that just because I want you to continue watching the video. I genuinely think if you're constantly faced with stuff that you find hard to understand, but you're trying to understand it, it's actually a really good thing, even if the information doesn't go in. And you should try and put yourself in those situations. So what will happen is that over time you will slowly absorb information just by being exposed to that kind of stuff, and much more quickly than you can imagine, that kind of information ends up getting absorbed. So if there's one piece of advice that I can give unsolicited to the world, it is just make sure that you put yourself in front of things that are hard for you, that aren't easy on first. Like you can't just instantly get it, because the stuff you get instantly is probably not worth a whole lot to you. And the stuff that's hard, well, especially if you're interested in it, that's where the real value is going to be. Okay, I'm just going to take a quick look at the chat here. So Caribou says, can you double the data rate by low to high 2? Yes, you can. That's literally what DDR stands for, right? If you know DDR memory, like RAM that you plug in, that's double data rate. And that just means that you are clocking data on the rising and the falling edge of the clock. There are some limitations that you get into when you start getting really fast speeds of transmission. And that gets really complicated, and I'm not going to go into any of like the high frequency communication stuff at the moment. All of this is really fast, like in terms of like comparing it to the Bus Pirate, for example. But we're still, I think this chip can really only transmit, depending on what mode you're in, but if you're in a serial mode, I think really you're kind of maybe looking at like 8 megabytes per second, which is really fast, or like 8 megabits per second, 8 megahertz, something like that. But that's kind of, yeah, that's still slow in terms of transmitting data. I think you can go faster if you use some of the other modes that I won't speak about today, but are really cool, like the FIFO mode. There you can transmit, I think, almost like almost native USB speed. All right, what's the issue with sampling on both rising and falling edge? Can't we have higher frequency on the data line? Again, yeah, you can do it. It's possible. All right, so now that we've seen a bit of this, I actually want to show you some of the code that I've written, and I want to actually show you this device. So maybe I can just do that in person first. This is one of those boards. Camera focus, will it do it? I'm not sure. Let's go really close and then come out a bit. Anyway, I think there's a bit of focus on there. This is the board. You can see it's pretty small, right? This chip is really small. It's like about a square centimeter, something like that. And yeah, it's a really nice board. It's cheaper than the Bus Pirate. Obviously, I'm not even sharing any links for this thing, but even if I was, I wouldn't be making money from it. I just really love this hardware. And one of the things I've done in the last couple of days to make working with this device easier is to design a second level of breakout board for it, which is kind of funny. It's already a breakout board. But I've designed this board, which is really just, you know, some wires, right? It's just making it easier to connect. And the idea is that this breaks out a bunch of common interfaces. So this one's I2C, this is JTAG, and there's SPI on the end. And what you do is you just plug in the FTDI chip there in the middle. And it's really easy to connect wires in and clip out, just get onto the signals that you're interested in. Instead of just go like, otherwise you have to figure out like, okay, which pins do I need to connect to? They don't have names and it's not easy to figure out. So yeah, that's just a small convenience. All right, so what I want to do is I want to hook this up with a little I2C device that I have on my desk and run a program that will enumerate all of the I2C devices it can find. And we'll do all of that from Node, instructing this chip on how to work. So if you just bear with me for the briefest of seconds, I need to hook it up. Should only take a second with this nice board. So there is that. And what we'll do as well is to hook up the logic analyzer in a little bit, and we'll actually watch what this is doing as we send it out. So I've got a little I2C device. I don't really remember what this one is. It doesn't really matter for this demo. Like, we're not going to be exploring the device itself. We're just going to be figuring out what devices are out there, like, connected. So I think it's some sort of like time of flight sensor, like distance sensor, but it might be something else. It's hard to tell. It doesn't have any markings on it. Okay, and I'll just already hook this up to the logic analyzer so that we can watch the signals as they go by. So that's going to be the clock. And that's going to be the data. Alright, so this thing is like hooked up now. It should be ready to go with the logic analyzer as well. Try to do as much preparation on this as possible, but there's always connecting the wires, right? Alright, so let me go over to the code. I'm just looking at the chat here. Greg says, where did you get that breakout board printed? Yeah, I used JLC PCB. They're the only PCB manufacturer I've ever actually used. It's really easy and it's really cheap. It's surprisingly cheap. It feels like it shouldn't be possible to get boards printed out this cheaply, but it is. It's just something, I designed it in KiCad, but yeah, it's literally, it doesn't even have any components on it. It's really just something that breaks out a bunch of things on header pins. So it wasn't a particularly advanced construction. All right, so here in this repository, I've got some test code. And one of the files I have in here is called I2C scan. And so what this program does is it instructs the FTDI chip to scan the I2C bus. And we're going to go into what that means in a second. So we're going to scan the I2C bus, and we're going to figure out if there's anything out there. I2C is a serial protocol, right? Just like the ones we've been looking at in this diagram. And it's a specific kind of serial protocol where it has, you know, a special way of saying that a transaction is starting. It has a special way of getting acknowledgement on both sides of the transaction. It's an addressed protocol, so every device that is on the I2C bus has an address. It's what's called a master-slave topology. I like to think of it as a main subordinate thing. So you have like a main controller and you have a bunch of subordinate devices. And that is because, like, you know, well, in I2C it's a little bit less so, but, you know, sometimes it doesn't always describe the two-way relationship in the best way. So I think that's better terminology, and also for other reasons. But yeah, I'm not going to go into that now. So it's a kind of main subordinate relationship, and what we do from the FTDI chip is basically we enumerate every address on the I2C bus. So there's a small address space, right, in I2C. You have 7-bit addresses, and yeah, we basically scan through 128 or 127 addresses. There's actually even less than that. But yeah, so we scan through some number of devices, not too many, and we just figure out if there's anything out there. That's pretty much it, and I'll go in a little bit deeper about that in a bit. But yeah, so Greg says, Bifrost, love the name. Yeah, I was trying to think of a nice name that would describe this project as a bridge, like a hardware bridge. And I was Googling around for, you know, like mythical bridges, and of course Bifrost is like the most famous mythical bridge. I feel kind of bad using this name because there's another project that uses the name Bifrost. This is also an open source project, but it's to do with like graphics driver reverse engineering and GPU reverse engineering, so I don't think anyone's going to get confused, and I think the fact that it's called FTDI Bifrost will probably also save that. But yeah, so all right, let's just take a little look into that. We've got a couple of this is actually all just JavaScript, so I would write TypeScript, and I will do that eventually, but because of the way that you do the Node native add-ons, it's really JavaScript first, and I'm gonna have to like layer on a level of TypeScript after that. And that's one of the things I might do in an upcoming stream. I might spend some time with you guys figuring that out, learning how to interact with Node native add-ons and TypeScript and getting those things to work correctly together. But also what we might just do is just abstract the whole thing, right, and add one more layer to, so we have the Node native backend, we have the JavaScript kind of bindings to it, and then we build one more library layer, which is kind of like the nice outside interface. And I want to do that anyway, so yeah, so we'll probably be doing that. All right, so we've got a couple of functions here. These are just like utility functions. I use them in like basically every video I've made for the past million years. If you've watched the USB videos recently, you'll know that USB devices have a vendor ID and a product ID, and those two things should uniquely identify the USB device, at least what kind of device it is, right? Because you have two of the same device, they'll have the same product and vendor IDs. This is the vendor ID for FTDI. If you work with FTDI stuff for a while, you will actually recognize this just by seeing these numbers, 0403. And 6014 is the product ID of the FT232. FT232H. Yeah. And then we've got some constants. These things are just defining some like literally some pins on the, that we have some of these physical pins. So pin 0 is what's known as pin D0 on the FTDI breakout board. D1 is this one, and this is D2, and these are just the numbers, right? And it would be good to expose constants for D1, D2, just like Arduino does for that kind of thing as well. So to get the well, we'll go into what the specifics of this mean kind of later. I think it's not the point of this to really understand how I2C and everything works in this one, but yeah, this is basically when we talk to the chip, we talk about directions, right? So when you have a pin, it could be an input or it can be an output, and when we have I2C, what we're saying is that the clock is an output and that we have a data output as well. And the thing is that I2C is it uses a bidirectional data line, so the same data line is used for data in and data out. But in this case, with the with this chip, we actually refer to those lines individually, even though they're connected together. So on this chip, on the breakout board, there's a little switch that says I2C mode, and when you click that I2C mode switch, it basically just connects the two pins, right? The data in and the data out pin. But as far as like us talking to the MPSSE is concerned, we have a separate line for data in and out. So that's the direction that we're defining here. We're saying that this pin, like the number of this pin, we shift a 1 into that position, and then the number of this pin, we shift a 1 into that position. So we end up kind of, basically what we're saying is we shift a 1 into the 0 position. So if this is a byte, we shift a 1 into that position, and then if this is another one, we shift that. So we're saying these two pins, like the physical pins on the output, these two are output and everything else is an input. And notice that this pin, which would refer to SDA in, is an input. But yeah, again, electrically, these two pins are connected together. All right. Just take a small look at the chat. I'd love a video about TS to write a Node native module. I didn't know Node native module supported TS. Great news. Well, the thing is, they don't, out of the box, they don't support it, right? So when you build a native module, you get a JavaScript interface out. But what you can do is you can build a .d.ts file, right? So you can build a file that that describes the interface that you've exposed, and then when that when this whole project gets loaded up by someone, when they npm install it, VS Code or any other kind of editor that is TypeScript aware is going to find that file and it's going to go, oh, okay, this describes the module, right? So what do I have? Oh, I've got this class FTDI Bifrost. These are the methods. This is the input and the output. But we have to layer that on externally. There might be some ways around that, but that's kind of how we end up doing it. Okay, then we got a bunch of functions, and we've got some more constants here. This is like the maximum number of I2C addresses, right? This is the highest I2C address that you can have. So when we search for them, we end up just searching till this point. Couple of just constants to mark whether something's a read or a write address. That's another thing in I2C. And then we have some more functions, right? So we've got a function here for getting a 3-phase clock divider value. We'll talk about that in a minute, but basically we can instruct the chip to talk at different frequencies. And it's nice if you can just talk about the frequency itself and not have to talk about like the weird number you have to provide to the chip. So there's some translation that has to be done, and basically this is the formula for the translation. And that formula is described in some documents that you can find from FTDI. So that I've kind of done the work already there. Then we have a bunch of functions here that are to do with just like basically writing commands. We'll take a look at that in a second as well. And down here we have the main function where we create an instance of the FTDI class. We do that by passing in the vendor ID and the product ID. I'll need to change this in the future because it could be the case that you have two of these plugged in and then there wouldn't be an easy way to differentiate. There are ways of differentiating in USB, right? So we can also pass the serial number, or we could just say take the first device or the second device or whatever. But right now I just assume that there's one device plugged in. Okay, so then this will throw an error if it doesn't work. So if we get to this point that we know that we at least established USB communication, then we figure out we figure out the clock rate that we want. So this is a 100 kilohertz clock, right? So 100 kilohertz. That's the frequency of the clock changing up and down. And we just pass that into this get three-phase clock value. And what this gives us back is a uint 16, an unsigned 16-bit number, right? So 100,000 already doesn't fit in 16 bits. So we can't just pass that to the chip. We only have 16 bits. Instead, what we describe is like some part of the equation that it had up there so that it can get back to that 100,000 cycles per second. Like we provide a smaller number that basically gets us there. The clock divider value. It's not even really a clock divider value, but yeah, essentially. And then what we can do is we can write data to the device. And by default, when we initialize the device, behind the scenes in the kind of constructor that happens for this class, that puts the device into the MPSSE mode, the multi-protocol synchronous serial engine mode. And so then we can just start sending it commands. And so these are the commands. And if we go back here to the top, you can see I'm just importing all of these commands from the module itself. In the future, I want to wrap a much nicer interface around all of this, right? I want to have methods that you call for the individual commands and that kind of thing. But for now, what we basically do is we build up a buffer of data and we send it to the device. And the buffer of data is just consists of these commands. So the first command is set the clock divider. Then we take this value that we have, we pass the least significant byte, and then we pass the most significant byte. So this is like a 2-argument function, basically, you could think of it. Then we do something called loopback end, which is just a specific command about how it does things internally on the chip. We don't need to worry about it for now. And we have this other command called drive open collector, which is something that is specifically for the I2C bus, which is related to how the electrical signaling works. And it's basically like in I2C, all the devices are connected to the same wire, like the data and the clock wire. And when the device wants to send data, or anyone wants to send data, they kind of take control of the wire, so to speak. Everything else should act as if it's disconnected. And that's what this whole thing is kind of doing here. The open collector mode, that's something to do with that. So basically we're saying drive the open collector mode, and these are the pins that we're interested in doing it on. So drive open collector on the clock, drive open collector on the input and the output, which again, these two are the same pin, but this is how it works internally. And the second part, the second argument, so to speak, is actually for that second row of pins. So that like we have a set of pins for D. We have 8 pins that are labeled D0 to D7. And then there are another set of pins that are labeled C0 to C9. So we have 10 additional pins that we can use there. But we don't do anything with those pins. Okay, so then when we write data, that immediately kind of sends that data out to the device. So if there was a problem in the meantime, and there can be problems, right? If you send a command and something isn't valid with that command, there will be an error, so it will throw an error. So you could wrap this in a try-catch, and you could catch the error, and you could figure out what went wrong, because this library does already give information back, like, hey, you tried to do this thing, this went wrong. But in this example, I'm not catching any errors or anything, because it would add a lot of noise in. So then I add a small delay. I don't know if this is strictly necessary, but I saw it in some other examples, and so I've copied it. But I haven't experimentally checked whether this delay is necessary and how short it can be. But this is a 50 millisecond delay. And then we send another command, and this is one of the most popular commands that you'll see. It's called, not popular commands, it's one of the ones you'll use the most, set bit slow. So this is basically us writing information to the pins. So it's called set bit slow because we're setting the D pins, right? The lower part of these 18 pins. And if we used set bits high, we'd be setting the C pins, right? So in setting these pins, what we're saying is we want the clock line to go high, we want the data line to go high, and you can see what we're doing is we're building an 8-bit number in the same way that I showed above, and in the same way that I've showed in a lot of my other videos. If you want to see how some of that works, you can look at like the bits and bytes of binary playlist that I have on this channel. That will explain how some of this kind of stuff works. But basically what we're doing is we're taking like the pin number and we're putting a 1 in that pin number position. So we're saying that these two pins are going to be high. They're going to have like a logic level high. And every time you do this, you can set the pin directions. So you can set whether something's an input or an output every time you're like clocking data in and out of the device. So in this case, we just use this predefined I2C direction constant, which defines like the direction of the pins, and we did that in the beginning. We use it all the time basically, so this just gets wrapped into a name. Then we have another little delay, and then we actually go into the search function. And so what the search function does is it has an array that keeps track of like every device, every possible address, and whether or not that there is a device at that address. Then we have two local variables. These could be inside the loop. I just put them outside for the sake of it, but this is basically things we keep track of every time we're looping around. And then we do a for loop from the start address up until the maximum address, and we just increment through each one. And yeah, basically in I2C, some addresses are read addresses and some addresses are write addresses, and that's what this if statement is basically checking. It's saying, oh, is this address, does it fall into this range? Oh, in that case, it's a read bit. We're going to do a read or a write. I'm actually not sure, so I'm going to zip back to the web browser, have the I2C web page open here, and we're looking at this table. This basically describes like the bits that we send out in each kind of I2C packet. And so we have the start, we send the address, and then there's 1 bit here, so you can see the address is 7 bits, and then you have 1 extra bit that describes whether something's a read or a write. So if the value is a 1, then it's a read, and if the value is a 0, then it's a write. And this, yeah, there are some more specifics about how the reads and writes work, but yeah, we'll get into that at some point. So that forms a full byte, you can imagine. All right, so if it falls into this address range, it's a 1, and otherwise it's a 0, and that defines our read write. So we call this function here I2C start, and that kind of sets up the start condition. That's exactly what I was talking about earlier, right? In the kind of abstract serial protocol sense, there's something that happens on the clock and the data lines, or just the clock line or just the data line, that is an indication to all the devices on the bus that a transaction is about to happen. And if we go and look at this function, what we can see is that it uses 2 of these set bit slow commands. And in the first one, what we're saying is we want the clock signal only to be high. So that means the data signal is all low. But yeah, the clock signal is definitely high. We have the standard set of directions. And then in the next kind of clock period, we're pulling everything low. So the clock signal goes low, every line is low that we control. And that's the start condition. So we do that, and then we send a byte. And what we do is we send a byte to a particular address, and this is a really low level protocol for I2C. So it's not like send a byte to an address. We're literally just sending a byte out on the bus. And so the byte that we send is the address shifted up by one place, and then the read or the write bit on the end. And if we look again at the Wikipedia article, that is the structure here. So we have these 7 bytes. These top 7 bytes, 7 bits, sorry, are the address, and then this bottom bit refers to the read or the write. So what we can do is we can take the address, shift it up, so it's at the top, these positions, and then we put the read write bit here, and that's exactly what we're doing in the code there. Take our address, shift it by one place, and put in the read write bit. We send that out on the bus, and we get an acknowledgement response. So when we send a message out, the device, if it's there, it's going to acknowledge us. And if it's not there, or it doesn't want to speak to us, it's going to not acknowledge us. And so the way that works is we have an ACK here, right? That's the next bit, right? Or it's not specifically a bit, but it's the next thing that comes out on the line. And it's pretty clever how it works, and I'll show you when we go to the logic analyzer kind of how that looks physically. But we get an acknowledgement, and if we get any kind of acknowledgement on an address, that's all we care about. That means for us that there is a device out there, and there is something that is responding on that address. And so we've kind of figured out, okay, there's something there. That's a valid address. So in this case, in the way that just in the way that the protocol works, if we get a 0 back, that means that there was an acknowledgement. And so what we do is we just set the address at that place to one of these two values, 1 or 2. So if it's a 0, no device at that address. If it's a 1, then we found a read address. If we found a 2, then if it was a read, anyway, we set a 2 if there is a write address then. And then we do a stop condition, and the stop condition is very similar to the start condition. It's a series of setting bits. So in the first case, we just make sure all the bits are low. Then we pull up the clock pin, and then again we pull the clock pin up and the output. And that's kind of that. Those 3 things kind of mark the end of a I2C transaction. And of course, if you're wondering, this part, this send byte and check the acknowledge, well, the way that works is a little bit more complicated because we need to both read and write from the device. But basically, we send some new commands at this point. So we send a kind of compound command at this point. We're going to do a write, and we tell the engine that the write should occur on the negative edge of the clock. And let's just break this apart a little bit to get an idea of what this means. This is different from set bits low. In set bits low, we're explicitly just saying put this bit to a high, put this bit to a low. When we do a write to the multi-protocol synchronous serial engine, that means we're taking data that's made up of many bits and we're sending it out across the lines, and that means it's going to enact the clock, and it's going to figure out when to put that data on the clock. And so that's kind of what we're describing with this compound command. We're saying both do a write and do it on the negative edge, and both of these obviously are just numbers, and so we can OR them together and we can get something that makes sense. And so what we're doing here is we're saying we're going to do a write. These next two bytes, they refer together as a unsigned 16-bit integer as the length of the transmission, right? The number of bytes we're sending. And much like the bus pirate, and much like Koi, if you also watched the Koi videos, this doesn't waste the 0 position to say not sending any data, because that doesn't make sense. If you send 0, that means you're sending 1. If you send 1, that means you're sending 2. So basically whatever you put here plus 1, that's what the number of bytes you're sending. So you don't waste any like kind of unnecessary bits. We send it out, and then at the end of the transmission, we do a set bits low. We set everything to a 0, but this is kind of tricky and it's part of I2C. We don't kind of set the directions to everything. We actually say only the clock is an output, everything else is an input, even SDA out at this point. Then we do another transmission. I think these could actually be in the same write data, but this means you would get an error. You would get an error if this one went wrong, you get an error if this went wrong, but it doesn't really matter. You could put them in the same. At this point, we're going to do a read, and we're going to read, again, we're saying we're going to read 0, but we're actually going to read 1. And notice that this time we're doing a read, and we're doing it in bit mode. So we're not reading a byte, we're reading a bit. So this engine can do all this kind of interesting, crazy stuff. And we're reading 1 bit. If you do byte mode, it's something different, and you can end up specifying more information. But in this case, we're just reading the 1 bit. So we get the 1 bit, and then we set the bits low. And that means we're just setting this one as an output and the regular direction. So even the clock is low at this point. And then what we do is we do this send immediate, which is a command that tells the engine, just flush everything you have out right now, like don't wait any time, because we want to immediately start trying to read back the result. Now, because of the way that, because of just like the nature of things taking time, but also the nature of I2C and like the kind of, how do you say it? The subordinate device is going to be sending us data at some point. We want to try to read a bunch of times until we maybe get something. So we try a bunch of times. So there's, and this whole thing involves like node buffers and that kind of stuff. And so like this is something, again, I want to put a wrapper around. But we try to do a read, and we check the status with that. All right, I think the stream dropped for a second there, so yeah, hopefully you guys didn't get completely disconnected. In any case, we do this read loop. It's a very low-level loop, so we're really pulling data in, and we need to mask it off and all kinds of stuff. But eventually, when we do this, we end up getting 1 bit back, and that 1 bit is the acknowledge bit. So that is kind of the essence of that. I don't expect this all to sink in and that you understand I2C and can go and build a low-level I2C thing yourself after this, but it's just to get a feeling for the kind of interaction that we have with this chip, the kind of commands that we can send to it. There are a lot more commands than this, by the way, but this is just one of the ones that we can see. So after this, it kind of does it kind of loops through all the devices we found, and it builds up a nice picture of what we have and whether we have a read or a write. So let's actually run this code. And I think the way I'm going to do it is I'm just going to run it here in this terminal. So let's go into the test code directory and let's run node i2c scan. So I'm going to run it, and I really hope it works. So yes, so if you can see here, we open the device successfully, so that's already a good sign. We set up the clock and the open collector. We are then searching through all the devices, and then we get this report of the devices. And this is an address space, right? So these refer to a hexadecimal byte. So 00 is this position. 45 is kind of this position. And what you can see here is that there are a whole bunch of dots, and the dots represent like no response, like we didn't find anything at that address. But what you will see is here at 2.9 we found a write address, and that is the address of the device that I have connected to the bus here. So that's actually something really cool, I think. This is all done in JavaScript, and we're fully communicating with this high-speed USB device that's doing like multi-protocol serial stuff. We can fully configure all of the multi-protocol serial engine stuff from this. So we could build I2C, we could build SPI, we could build JTAG. We can build any kind of serial interface now, and that's already working. Both reading and writing data already working. So let's get a picture of this. Let's get a picture of this like in physical terms. So let me go and find logic, and I need to figure out where that is. I think it doesn't seem to be working, so I'm going to check here that in OBS logic. Yes, I think it should be visible now. Apologies for that. Okay, so I already have this set up in I2C mode. I've got the device connected and I've got the wires connected. So if all goes well, this should actually work. What I'm going to do is I'm going to start a scan, and then I'm going to run the program again. So I'm going to do that as fast as I can, switching windows, press play, run the program, stop. And if I zoom out, you can see that there is this just tiny little bit of time where there is some data on the line here. And if I zoom in, you can see that there's a whole bunch of stuff been transmitted. So this is our clock on top, and the data is just below that. So that gives you a sense of how fast this is. This is a clock period of 18.68 microseconds. Sorry, the clock period is 37.56 microseconds. So that's pretty fast. It's way faster already, I think, than some of the stuff we did on the Bus Pirate. Maybe not the actual transmission speeds. I think the Bus Pirate can go this fast, but what it can't do is send it all at once. The Bus Pirate would insert these big gaps where it's buffering data. So this is already a big plus on that sense. But what we see here is the I2C data being transmitted. And one of the cool things about this is a Salier logic analyzer. This is not a sponsored video, but you can get a really good deal on these things. So this is a Salier logic analyzer. This is the software that Salier makes, and they have something called protocol analyzers. And I have an I2C protocol analyzer installed on this thing, and so basically it is decoding the information for me in real time and providing all that data. And you can also just see it in raw form, right? So you can see that there was a write to this address and we got a NAC. And then there was a write to this address and we got a NAC. And if we scroll down to 29, where we saw in this big table, where we saw in the code output this table, what we see here is a write to 29 and we got an ACK. So that's actually the that's the same data coming back. But let's just zoom in here and see how this I2C transaction looks. Here we see that the clock, this is the clock, this is the data. The clock starts high, so it idles in the high position, and then it drops to the low position. And also at the same time, the data drops to the low position. This whole thing with open collector means that, well, if you read into I2C a bit, what happens is kind of devices act as if they're not connected to this line. They're all connected to that same line, but they kind of disconnect from the data line. And the data line has something called a pull-up resistor on it. So basically what that means, if nothing else is kind of driving the circuit, if it's not driving low or high, so taking control of the electrical line, then the line will be pulled up to a kind of default value, if you will, and the default value is high. And so what happens is when the clock goes low and the data goes low, it's very clear to all the devices electrically that actually, yeah, something is taking control. There's a transmission coming because that line would be high by default. So the fact that it goes low is the indication. Then there's some period of time, and then the clock starts pulsing. And we're pulsing data out, and we're pulsing out on the negative edge. So just like the example I showed, and all of the data we're sending out is 0, right? We're writing the address here. So 0, 0, 0, 0, 0, 0, 0. And then on this last one, whether it's a read or a write, we're actually sending out a 1. Because if we look here on the web page, this must be a write address. And so we need to send, sorry, this must be a read address. Let me take a look. Should have done some more. So it's a write, but somehow maybe I'm missing it. Oh, okay. Right. If we zoom in, the line goes high afterwards. So please disregard that. That's just my extreme unpreparedness here. So here at this last period, it also reads a 0. So it's all zeros. We're doing a write. A write is a 0. But then what happens is we tell the engine through those commands that we have to actually, after we finish sending, to actually pull up or like to release control of the data line. So the data line ends up being pulled up high by the device. And so then later on, when we send this one clock pulse to kind of read in whether or not there was an acknowledgement. I don't know if it's when we send this clock pulse or not. I need to take a look on we'll see when we get to 29. But you can see basically we don't get an acknowledgement. So that's why a 1 is a knack, right? A not acknowledge, because the line is high by default. So we're pulling it down 0. That's the device explicitly driving the line and saying, no, I acknowledge your request. So in this case, it stays high. And I think at this point, that's us kind of like asserting the stop condition. So we end up driving the line down ourselves. We push the clock high, and that's kind of the stop condition of the whole thing. And then again, we dive into the next transition. So here again, we're sending the address out. So 0, 0, 0, 0, 0, 0. And in this case, this one ends up being a 1, right? Because we got a 1 here. And then again, here, if we zoom in, this is driving a 0 at the same time. Yeah, sorry, that would be a 0. So this one is the read-write bit, and this is the final address bit. So I guess that reads, that actually reads a 1 at that point. Maybe if we zoom in really close, no, we don't see it. I could probably sample faster, but don't see it. All right, so let's zoom out and let's actually take a look at. It's interesting that there is this little gap here. I wonder what that is. Oh, anyway, so where is 2.9? Okay, so this is 2.9. All right, so we start the transaction, we send out the address, and then we send out the read-write bit. And then at this point, the line is, so this is the 29. So the line is high, but it's then driven low. And this is the device acknowledging us. I think, yeah, indeed, this is the device acknowledging us when at this point, right? So the line gets driven low, and then the FTDI chip, that's us pulling the line high after we get the data. All right, so that's pretty much it. That is the electrical part of this whole thing. I hope some of that was clear. It was a little bit ad hoc, but yeah, that's kind of where that is going. And I actually wanted to show another demo, but I'm going to skip it for now because I want to keep this stream pretty short this evening, at least short in terms of the ones I've been doing lately. And I want to show some of the code that kind of underlies this, right? The node code. Do those gaps correlate to the delays you have in the code? So some of them do. Let me take a look. So there are some delays. Like there is a delay in the, let's actually go there in the code. So none of these have delays. The I2C start stops. The only place there was a delay here, right, in the loop, but I took that out at some point because I just wanted to run it at the maximum possible speed. So I think those delays, those are just some like buffering moments that the chip is doing. It might be like, in those cases, it might even be like a temperature dependency or like a, you know, just general conditions. I'm not sure about the variation there. And I think depending on what kind of mode you're in and how you're sending the data out, like the chip will buffer up more data or less data. And so like if you actually go and send like a large chunk of data, I think this device can buffer up like at least 1 kilobyte, or I think like 4 kilobytes of data at a time, which is a lot, right? If you remember that the bus pirate can only send out 16 bits at a time, or 16 bytes at a time, the fact that like this FTDI chip can buffer up like 4K bytes at a time, that's pretty good. If you stream those out, you'll see that it goes pretty much flawlessly. Like it streams them out like everything clocked perfectly on time. I think it's to do with like the fact that we're sending out, like not delays, but when we do the send immediate stuff, I think it's like that's it, kind of having these flush moments where it might have to do some things internally. I don't know how the hardware is built for this thing, so it's kind of hard to say what it's doing, but that would be my guess. Right, so that's the I2C scan in JavaScript, and maybe the first thing that's useful to do is to understand what this looks like if you actually write this in C, and that's like what the low-level library for talking to this device is written in. It's written in C. So let's take a look at that. This is the same program. I wrote this program first, and then I ported this over when I did the JavaScript stuff in order to have a kind of sane comparison point. So this is the I2C scan written in C. So it uses this FTDI library. This is not the official FTDI library. There is like an FTDI library released by FTDI, and I don't like that library very much. It's like backed with a driver, and the reason I don't like it is because it has a whole bunch of weird stuff, and there is like a driver that's loaded for FTDI on basically all computers, and in order to run this kind of code, which is basically a custom driver for whatever device you have attached, you actually have to like unload that driver. So you need all this root permission stuff in order to do all these kind of things, and I don't really like that. Instead, this is libftdi, which is an open source version of the driver. It's an open source reverse engineered driver. And that has been done in pretty much exactly the same way as the keyboard reverse engineering that I was doing was done, which is basically sniff the USB traffic as you send commands with the official driver. And someone, I think a bunch of people, a very long time ago as well, because these chips, they're not brand new, right? They've been out for a long time, like at least 10, 15 years. And, well, some of them even longer than that. And people have reverse engineered them a long time ago using those techniques. Again, not new techniques. But yeah, so this is the open source one. It's built on libUSB, which we've spoken about previously. And yeah, so this is a really nice driver, a really nice open source library. Again, you can see the vendor ID, the product ID. You can see all the same constants that we had in the other program because it's doing the same thing. And the big difference that you'll see is that in the main function for this, like we end up creating an FTDI object. It's there's something called an FTDI context. Maybe I can open it here. It's a big object that has a whole bunch of like fields on it. You can imagine this being just like a JavaScript object, right? It's got some USB data. It's got some like things for USB. It's got a whole bunch of FTDI specific stuff. It's got like information about which chip it is and which kind of mode we're in and all that kind of stuff. So it's just an object which describes it. And we use that object. It's kind of like a class. Kind of. In C you don't have classes obviously, but basically all the functions that we call, we end up passing this in as our context. And every function is called relative to that context. So we have something, we have in C also there's no error throwing and all of that kind of stuff. What you have is functions returning you an error code for whether something went right or wrong, and the code corresponds to some specific thing that went right or wrong. And so we keep track of that here with a variable that's able to understand the status of every function call. We use this integer variable to keep track of like a position in a buffer. I'll show you that in a minute, but I used the same technique a lot in the virtual machine series when we were writing machine code into a buffer by hand. Basically you use this as your index and you increment it every time, so you don't have to say index 0, index 1, all that kind of stuff. And then we have a buffer that we're going to write our commands into. So this is just exactly the same as in Node here, right? We use buffer.from, so we don't have to manually allocate buffers and that kind of thing, but we're still buffering up data. So it's the same thing. We need just a big buffer of space to send into the chip. So we create a new context, we check if it worked, then we try and open the USB device, we check if it worked, and then we run some code that initializes the chip itself, right? So there are some calls we need to make to like reset USB and then set the interface and set up MPSSE mode, all of that kind of stuff. That gets taken care of in the constructor for the library, but in C, you need to do this stuff manually. And obviously in the library as well, I also want to expose basically all of these functions as well, and I do expose some of them, because there are other modes that you can go into. You don't just have to use the MPSSE mode. There are also other modes you can go into and do cool things with. So then we do the same sleep for 50 milliseconds. And then, yeah, what you can see basically here is going to be exactly the equivalent of these initialization things we did here. So like setting up the clock divisor and the open collector and everything. Except in C, it's just much more verbose. We have to write into each individual byte. But what you can see is we're sending the same kind of command. So in this case, we're enabling 3-phase clocking. I think we do this stuff. What do we do this stuff here? Oh, I think that's actually a bug. I'm actually enabling 3-phase clocking. I should be doing that somewhere. Anyway, okay, that's just a problem with my code, but we should be doing that kind of stuff here. And then we're setting up the clock here in the same way. So we set up the clock divisor. I pre-computed this value, but it's 100 kilohertz. Setting up loopback end, driving the open collector. So I basically went through the process of working out all these commands and everything on this one. And as we get to the bottom here, there are also some functions for like set I2C start condition, I2C stop condition, send byte and acknowledge. All the same functions that we have in the JavaScript code we have here in the C code. So it's all kind of the same. You can see that fundamentally all of the big operations we do are pretty much exactly the same. The big differences are that in every function call where we do something with the FTDI device, we have to pass in this context object, and we have to pass in a buffer, which is basically holding the data. Oh, I see that actually the stream has stopped. I hope that's coming back. All right, I think it's back. In every case, we send the buffer, and we also pass a reference to this status variable so that it can get written like by the calls we make. But yeah, so in some places we're dealing with pointers to things and holding references, and we have to have more low-level association with like, okay, we've got this buffer, we have this number of bytes in it, which we don't have to worry about in JavaScript, but everything else is pretty much the same. So that gives you a sense of like kind of the FTDI side of things. And then let's just take a small glance into the actual Node add-on code itself. I'm not an expert in like Node add-ons. I'm not a C++ expert. This is my first time building a Node add-on, and it's not that bad, right? That's one of the things that I've figured out while going through this process. It's actually pretty doable. It's tricky because there is a lot of information out there on the internet. Some of it is outdated, and some of it is like based on a very low level interface to like Node and V8. What I'm doing is I'm using something called the Node add-on API. It's actually from Node, but it's like a slightly higher level way of building the add-ons. And so everything you do is part of this NAPI thing, which stands for the Node add-on API. So kind of what happens here, this is the main file. This is where we define the Node module itself, right? So like we're going to have, like when we come to import something in JavaScript and we use require and we say pull in this thing, like these things, we're defining those in this main file. So we have this function called init. It returns a Node API object. Whenever you see this in C++, this just means namespace. So like this is an object in the context of this namespace. It's a little bit tricky stuff, but you can imagine like in JavaScript, we'd be saying something like we have a Node API dot object. This is the return type. So we're returning an object. And this is the name of the function. And this is the stuff that gets passed into the function. Now we don't pass this stuff ourselves. Node injects this in. And the way it works is we define this function here, the init function, and then we call this this function, so to speak. It's a macro, but it doesn't matter. This registers our module, right? So it says the init function, that's going to describe our module, and our module is called ftdi_bifrost. And so that bifrost thing, that's defined in another file, the binding.gyp. So whether you know about Node add-ons or extensions or whatever, whether you know about it or not, you've probably heard of Node gyp, because it's something that you see when you install packages sometimes, and especially packages from the early days of like the Node ecosystem, things like Node SAS. If you worked on like web front-end technology, you'd see like Node SAS, and it would, like when you would install it, it would take ages, and all this information about Node gyp would come up on your screen. Maybe you would have trouble installing it, and you would have to debug those issues. But basically, Node gyp is like this tool for creating this whole interface and defining all of the metadata around your package. And so every Node add-on has a binding.gyp file, which is like a loosely JSON-esque language, where you basically it's got like a kind of domain-specific language where you describe this stuff. So it describes like things that get passed to the C compiler and the C++ compiler, specific libraries that you need to include, the name of the target. This is where we get that name from, that ftdi_bifrost. This name here has to match with this name here. We register our source files in here, so all of the C files or the C++ files that we have, we register them here, and then the compiler knows where to find those and where to build them. And like any things you might need to pass to the linker as well, All of this stuff, if you don't know too much about this, it doesn't really matter. Like, if you come to build extensions, you will have to learn a bit about C and build systems and C++. Probably won't need to go too deep into the linker, but you will need to work out which flags you need to pass to it every now and again to get it to make sure your libraries connect with it properly. But this is the binding zip folder file. And yeah, this is pretty much it. So this function, what we do is, well, you always have to do this handle scope thing. It's just part of the thing. Before I get into this, I think something that's really important to understand about the way that these node add-on works, these node add-on things works, is that there is kind of like two worlds that you have to bridge, right? It's like a second bridging thing here. I guess there are like you can think of it being three worlds that you're bridging together. On the one side, you have something like a library that exists in C or C++. So in our case, that's the FTDI stuff. So we want to build a bridge into the node add-on world for that. So in order to do that, we have to, bring it in. We have to include its header file, and we have to kind of write some functions that can talk to the actual C++ V8 node API stuff that exists. That's the first bridge. And then the second bridge is that you have to take this world, this C++ world, or C world, depending on what kind of libraries you're using, but the node add-on itself is written in C++. You have to somehow connect that into JavaScript. So like if you think about, like, we might want to do some calculations here, we might want to crunch some numbers, and so in C++ world we've got numbers like uint32, uint64, uint8 for a byte. We might have a float value or a double value that holds like a decimal, a floating point number. We can have any of these kind of things and a lot more. But in JavaScript, we've just got one number type, and it's called number. Of course, we have uint8 arrays and typed arrays, that kind of stuff, buffers in Node. But by and large, we have one number in JavaScript. So if you want to take a number that you have in C++ world and somehow get it to live in JavaScript world, well, you have to wrap it up into a special thing that, a special wrapper that exists for the Node API, sort of like the way you get things into the thing. So this is what all of these things from the Node API are from, like the object. Like that's like a JavaScript object. That's how you can think of this being an actual JavaScript object, because it's the object that we end up pulling stuff out of here. And likewise, we can just go into this a bit. Node API, we can have things like an array or an array buffer or a big int 64 array. There are all of these data view. There are all of these data types that exist in JavaScript, and we have ways of turning C++ things into those JavaScript things. So if I were to do this, right, make a number n. So this is now a C++ number n. Well, we can call a method on that, right? So we can say, how can we do this? We can say, like n equals napi number new. So we create a new number, and we pass in the environment. So that's kind of like the context of the whole, kind of extension that you're running in, the kind of like the process context, if you will. So we pass in the environment, we get that from the outside, and then we can just pass in a double at this point, right? So we could, we can say 3.142, and now what we've done is create a number in the C++ world that is ready to go into the JavaScript world, right? And you can get numbers in and out. You can create numbers. You can say what do we have here? n.from, and then this is so we could do something like that. We could say we have a uint32t, and then we could pass in some number here. So we always need to pass in the environment, but this is another way we could do it. So like when we do this, we're kind of creating a number based on this type. So yeah, that's kind of one of the things that's important here. Like we've got a way of turning JavaScript values into C++ values, and a way to turn C++ values into JavaScript values. Okay, so two things we do here. Well, one simple thing is that we define a whole bunch of constants. So all of these constants, they are the things that we're like pulling out of here, right? The tclock divisor, the mpsse do write, and write negative, that kind of stuff. All of these constants, they actually exist in this FTDI library. So if I open this up and we just kind of like pull the, if we scan down it, this is just a header file, but you'll see it contains a whole bunch of these defines, right? These are all just numbers. And so here what we're doing is we're just saying, right, expose these to JavaScript. And this define constant is a macro, which just basically puts that number into the context of JavaScript, using some like this ends up expanding out into a couple of lines of JavaScript, basically, of C++. And it's just easier to do it this way. I borrowed quite a lot of this code, especially these macros like define constant and a few of the other ones that you'll see. I borrowed and based quite a lot of my code on the Node USB code. So Node USB is the USB bindings for Node that we've been using to write the USB keyboard driver, for example. I use that as my main reference point for learning how to write these Node extensions. The code there is pretty readable, and if you're looking to get into this, I would recommend reading their code because they do a lot of nice stuff. The tricky thing is with these kind of macros is that you really need to like recognize that there's a macro and go and read it and figure out kind of what they're doing. You need to learn a little bit about how macros work. They're kind of tricky. They can be tricky if you do certain things, and this library does some things that I would consider to be tricky. Like, I don't see anything in this particular one, so don't worry about it, but something to look out for, but it's not too bad. So here we're calling this init constants function. It's just a function that I've put in this library. It's not something special. I've just built it here to abstract. It takes in an object called exports, right? That's what we're putting all of our things onto, and I'm just calling that with the exports so that like we can do all of this stuff somewhere outside of this little function. Now they're just the constants involved in the library. Obviously the real interesting stuff is this class that we have, the FTDI Bifrost class, and all of that stuff is done in this other file. So you can see that that I'm calling another init function, or it's actually a static method. I'm calling this init method on FTDI Bifrost, and that's kind of like a mirror image of this one as well, right? I think this also returns an object. It does, but we don't use the object directly. Yeah, what we're doing is we are initializing another level. So it's the same kind of initialization, but this time we provide the environment, the exports. And this just means that you don't have to like, this gives you a nice way of like separating out your different parts of your module, right? You don't have to put everything in one big file and say, oh, this is my whole module. You can define this part over here and this part over here and then connect it all together in this main file. So let's take a little look at this FTDI Bifrost class. So this is just the header. If you know a bit of C and C++, you'll know that code is split into header files and source files. And header files, they are kind of you declaring your interface to the outside world. And other files can include your header file, and it basically just declares information about what your class can do and what kind of things are inside your source file. But you can, yeah, it's not where the actual implementation goes. And I'm not going to go into all the reasons why you don't put those two things together like you do in other languages. Like most languages, you don't separate those two things. there is a really good reason for it, and it's to do with the way that the build works, and like the way that you actually build and like create units of kind of compilation between in the languages themselves. But in our case, what we do is in the header files we actually declare the interface. So I'm making a class here called FTDI Bifrost, and it inherits from this class from Node API called Object Wrap. And Object Wrap is kind of this really nice magical. It's like as far as I'm concerned, this is the most useful thing that I've come across in the whole library, especially of the way of making an interface. Object Wrap allows you to write a C++ class that kind of creates a wrapped JavaScript class. So when I create this FTDI Bifrost thing, I create it with a bunch of methods. So you can see all of these methods down here. And what I can do is I can actually map those methods into JavaScript directly using this class. I just have to do some registration code, and I'll show you that. So up here there are some kind of private variables. So we keep track of an FTDI context in this class. We keep track of a status variable, a vendor ID, and a product ID. So this is all the same stuff that you can see that we did in the like when we were looking at the I2C scam, right? We just needed all of this kind of information: the vendor ID, the product ID. We needed to keep track of an FTDI context and that kind of stuff. Same thing here. You'll notice we don't have a buffer here because that's done in a slightly different way. Let me just take a look at the chat here. Do those correlate to the delays? Oh, that was a previous message we already saw. Why is it all wrapped in if not def? Oh, do you mean this part, Greg? I think you probably mean this part. So this is a pattern that you see in C and C++. Yeah, so it means if not defined. So what's happening here is it's saying if this name has not yet been defined, define it. And also do all of this stuff down here and then end the define. So what happens is if this has been defined, then it's like none of the code will get generated. These are also part of what's called the preprocessor. So they're not part of the language itself, but they're part of the preprocessor of the language. It's kind of an interesting thing. So when you write C and C++ and you do include, what that basically does is that goes and finds the file that you want to include. So FTDI Bifrost in our case, right? It takes this this whole code and it like cuts it and it pastes it into the source. That is actually what the compiler does. And the problem with that is that, you know, your header files might include another header file, and you might have that header file somewhere else. Like I might include FTDI Bifrost and util, but FTDI Bifrost might also include util, right? That could happen. And what would happen in that case is that you just have two pieces of the same code copy pasted inside. And so by surrounding everything in these guards, they don't, like when it ends up generating your code through the preprocessor, even though it copy pastes the same code a couple of times, only the first instance would actually get inserted into the code, because everything else would evaluate this condition and say, oh, that's already defined, don't insert anything. So that's the reason that happens. It's a bit complicated. Well, it's not complicated, but it's a bit tricky if you don't know how the compilation process works. But that's basically the reason that happens. And there is something that I really wish that, you know, the world moves slower in C and C++, especially in C, but in C++ the world moves a bit slower than it does in something like JavaScript. There is something that you can do that is like this, right? Pragma once. And that's the same. That is like a non-standard way of getting rid of these things, right? The end if. all that says is to the preprocessor, only include this function once, right? This whole file once. The problem with that is that it's not supported by every single compiler. It's supported by pretty much every single compiler, but in that world, if something isn't standard and isn't supported by every single compiler, then it's pretty much advised against, even if it's the most common thing in the world. So I actually feel like doing this, especially in this compiler, I know 100% that if I use this in this code, this would work. But for the same reason that everyone else does, which is that people tell you not to do it, I don't do it. So that's why I haven't used it here. But you know, you get so used to seeing this as well that it kind of doesn't matter that much. Yes, I see that Kakeland is also mentioning the pragma ones. So that's pretty much that's that part. Right, so in this class, basically we keep track of the FTDI specific stuff, and we define a whole bunch of methods that are going to be exposed to the outside. We also define a constructor and a destructor. So in C++ you have destructors as well as constructors, and in destructors you can get rid of any memory that you allocated and that kind of stuff. And we need to implement this method, which is part of the object wrap, which is the init method. So this is just us telling like the Node API. Remember, we get tons of this stuff from Node API. So this is one of the things we need to implement, and you can see we call it here. So small recap. This whole class, we're defining a class here that will appear in JavaScript land, and we can do that by inheriting from this special thing called object wrap, which wraps up a C++ class and allows some of it to be exposed in a controlled way to JavaScript. In here we can define a whole bunch of methods, like actual just C++ methods that will be called, and those methods will be able to be mapped into JavaScript, but we also have to implement some other stuff. So if we just take one more look into the actual code itself, so this is not the header file anymore, this is the implementation file with all of the code that actually runs. Here you'll see we've got the init method. And in init method, what we do is we call a method on Bifrost, FTDI Bifrost, which is actually implemented by object wrap. It's a static method called define class. And what this does is it's a method where we provide the environment, we provide the name of the class, and then we provide a sort of inline object which defines all of the instance methods. So here we say, oh, we've got an instance method. We want it to, in JavaScript, we want it to be called WriteData with lowercase. And that just references this actual method on the class called WriteData. And then when we've done all of that, we set that in the exports. We literally just say FTDI Bifrost is whatever comes out of this thing. And then we return exports in the end. And I mean, that is literally what's happening here in the main class. When we call init, that is kind of registering that class into JavaScript world. So that's how this connection is made. Then for the actual data part, this is the constructor. So in the constructor, like most of what you'll end up seeing in this kind of code is just us like translating JavaScript world into C++ world and the other way around. So what we do is we get an environment, like to all of these methods, the constructor and the methods that we define, when these are called, they're called in the context of the Node API and of VA and the kind of running life cycle of that whole thing, right? We're just tapping into it. So when that's called, that is called with a special object called info, which is a callback info, and that kind of contains all the information you need to know about how this was called in JavaScript land. So which arguments was it called with? What were the types of those arguments? Were there any arguments? And it contains like the environment we're running in, all of that kind of stuff. So the first thing we do is unpack the environment, We do this handle scope thing, which is kind of, that is to do with the scoping rules of JavaScript. It's not really that important right now. And what we can do is we can check if we got enough arguments. It's funny, we actually have to write kind of JavaScript-esque guard code in C++ world, because in JavaScript you can call a function without the right number of arguments. That's what you can do there. So we need to check in this case if we got the right number of arguments, and if we didn't, we can actually kind of throw an error into JavaScript. So what we do is we get node API error and we create a new one in this environment. This is our error message, and then we call a function on that, or a method on that called throw as JavaScript exception. So we throw this into JavaScript, into its running thing, and we return. And I think there are ways where you can actually throw this as a C++ exception, and you can circumvent needing to call that kind of stuff, but I haven't looked too deeply into how that works. There are ways of doing it. I've seen that you can do it that way, and I'm pretty sure Node USB does it that way, but I found that I had to go down this route. Alright, so when we've checked the length of the arguments, the next thing you do in JavaScript obviously is you check the type of the arguments to make sure that they match. And of course we can do the same thing here. So we can just say, is argument 0 a number, and is argument 1 a number? And of course this is the vendor ID and the product ID, so they should be numbers. So that's kind of what's happening there. We're checking if they don't make sense, we're throwing another error. So all standard stuff. And this is where we do the kind of interesting part. This is where we unpack those values from JavaScript land into C++ land. So what we're doing is we're saying, take argument 0 and cast it to a number. So this, if you use TypeScript, C++ also has its own kind of generics. It's actually much more powerful than TypeScript's generics. They're called, in C++, they're called templates. And you can do more than just types. You can actually do values and all of that kind of thing. So it's really, really powerful generic system. But in this case, what we're doing is saying, take argument 0 and give it to me as if it were a JavaScript number, and then take that JavaScript number and cast it to an int32 value, so an actual integer value, and set that to be the vendor ID. And even though, like, in C++ you don't have to do this, right? In JavaScript we would say this.vid, but in C++ it's kind of in the context of this class. We don't need to give a name to it, so it's just vid equals. And really it would be better to put a naming convention on this kind of stuff, and that's what people do. They do something like mvid and mpid to say this is a member variable, but I haven't done that here. Then we're creating our FTDI instance. We're doing the same kind of error checking we were doing in the C file to make sure we actually got it. Then we can initialize it. Then we can open USB. And this is kind of why one of the cool things happens is we do this FT status. We do open USB. And if the status is negative, that means that there was some kind of error. And what we can actually do is ask the FTDI library what this exact error was, and we can get the string error message. So we can do that like this. We basically say, give me the error message as if it were a string with the current context. And because every context carries the error message of the last thing that happened, that's how we can do this. So then what we end up doing is basically throwing an exception that has kind of, an embedded specific exception. And yeah, I do that all over the place in this code. So like we get the actual errors that come from the library itself, and like useful error messages. Then we initialize the MPSSE in the exact way that we do it in the C program. So then we have the destructor. There we get rid of the FTDI memory that we used. So if we have an FTDI instance, we close the FTDI instance and we free the memory. That's just standard memory management stuff. And then here, now we have all the methods, right? So this is the method as it appears in JavaScript. So we say write data, we pass a buffer, and we say a length of that buffer. Like we say it could be like 5 bytes, like maybe the buffer is like a 64 byte buffer, but we only use 5 bytes, so you can pass the length here, but it's optional. That's the API I've provided in JavaScript. And so here what we do is, well, we end up, I'm using some macros that I borrowed from Node USB. So there's one called enter method. And enter method, what it does is it gets an environment, it calls handle scope, and then it checks that a certain number of arguments are present. And if you follow check arguments present, then you'll find that that's like doing some analysis and throwing an error. If you follow it all out, there's a whole bunch of code that ends up being inserted into that first part. But basically, we can just say we enter the method and there's one argument expected. We can check the type of that argument, so we can check if it was a buffer, and then we can throw an error and return. So that's a macro I wrote, and we just throw this error message. So we're just doing the same kind of checks. Here we end up unpacking that first argument, which again, it's a buffer. So we're saying, give me argument 0 as a node buffer of integers. And once we do that, we now have this buffer object, and we can get its length. And so we have a size of the buffer. We can check if we got a second argument, and if we did, we check it's a number, and we say, yep, that's the length of the buffer. We do some other error checking stuff here. But basically, if we didn't have that, we would have some sort of default length. So that's how you can do the default argument stuff that you get in JavaScript. And then eventually we're just calling the write data. And this is one of the really cool things that you have, right? So this is a node buffer, right? It's a node API buffer wrapping a uint8. And if we call data, that gives us a pointer to the actual data in the system. And that's what this FTDI library needs. It needs a pointer to where that data really is. And so that's really nice, right? It's a super straightforward thing to get the pointer of the data in C++ and read it out. And also, as we'll see in some other places, it's really easy to get the pointer of a buffer that is given to us by a user and then write data into that using pointers. So it's it's really, really nice from that kind of perspective. And what I really want to make clear is, like, most of what this whole library is doing is just doing all of the kind of housekeeping code that you need to do for Node API, doing a whole bunch of like checking to make sure that values that get passed in and out of functions are the types and the lengths that you expect, which is stuff you're used to doing in JavaScript anyway. And the actual kind of core of the code is just these sort of like these few lines here. And this is basically exactly what you see, exactly what is being done if you just write a C program that didn't do the whole Node API thing. So this is all pretty straightforward stuff in terms of what it allows. And once you know some of this stuff and you've kind of done it enough to be used to the kind of weird things you have to do, it really opens up a whole bunch of doors. It's like, wow, okay, there are so many libraries out there for C and C++ that do really crazy things and do them really, really efficiently. So if you kind of armed with this knowledge, you can actually think, oh, okay, I could actually port any of these libraries to a Node add-on and then just create this wrapped, object-wrapped interface to JavaScript, and I can just expose that to the world. And I think it's a really, really powerful technique that's kind of, most of the people who use the web ecosystem, most of the people that are writing code in Node or just even on the web, they're not really super aware of it. And I know I wasn't, I was aware of it, that it was possible, but I thought, this must be much harder than I think it is. But it's actually not that bad. So that's the write data. Everything else is mostly similar. In read data, there's something interesting that happens, is that you pass in a node buffer and you expect that data is going to be written into your buffer. So that's kind of an interesting thing. You're passing almost your own pointer in this case, right? I give you an array and you put stuff into that array for me. So that's kind of what happens here. And the interesting thing that happens there, right, is that we do all the same steps. We grab a reference to the buffer, and then we grab a reference to the pointer of the buffer, right? So this is a uint8 pointer to our that we call buffer raw, which is a pointer to this data, the actual data that the user passed us. And we can pass that to FTDI read data. And when you write into a buffer in the Node add-on, if you write into that from C++, it will actually reflect in JavaScript. So it's a really, really powerful technique. I mean, it's also a technique that you should be careful with, because in that case, you're getting into this is the place where you need to be aware of like how big your buffer is and make sure you don't write off the end of it, because things will go wrong if you do that. And maybe you'll create security problems if you do that. But it's very, very powerful technique. Pretty much everything works like this. It's just a bunch of stuff to do with JavaScript, checking and the ceremony of Node API, and then basically interfacing with your library. This is the technique. And that's it. I haven't even mapped that many. I haven't mapped in that many methods yet because I haven't needed them. But what you'll see is that so far I've got write data, read data, set the bit mode. So that allows us to not only speak in MPSSE mode, but also to speak in bitbang mode or FIFO mode or any of the other really cool stuff this chip will do that maybe we'll look at in the future. We can do get status, which actually just returns the status code that is returned by all of those things. It gives you access to this variable basically. We can set the baud rate. That's something that's only relevant in bitbang mode. And we can read the pins, which is also something that you do in bitbang mode, right? You read and write pins. So that's pretty much it. And I hope that this has been kind of a somewhat insightful interface as to how you can put one of these Node add-ons together that goes beyond like a hello world example, because as far as I can tell, there are not many like references that go anywhere beyond the first step of hello world online, especially on YouTube, but even in like tutorials and things. So I hope that I can actually, with these videos, I mean, this video for me is like a starting point. I kind of want to bring everyone up to speed with where I am. But I'm hoping to make some more that expand out and kind of make this side of things a little bit clearer for people. So I hope some of this has made sense. Maybe it's been a bit inspiring to try some of this stuff out. And yeah, so I think I'm going to start wrapping up the stream in a minute, so I'm going to check the chat for questions. I'm going to see if anyone has got any questions, and then I think I'm going to bid you a good night and a good weekend. And maybe if you come into the Discord channel that we have, you can find a link for the Discord server, below. If you find yourself playing around with any of this kind of stuff, hardware stuff, anything you've seen in the videos, just writing Node add-ons, that kind of stuff. There's a whole bunch of people that I think, would enjoy the conversation there. So including me. So check out the Discord if you're interested. Now I'm going to check the chat. So I see Greg. What is the development cycle like with this? I assume you have to recompile the C++ code every time you make a change before you set it in Node. Yeah, I can show you actually. I can show you what the compilation process looks like. So when you're in the context of a Node API, it installs a bunch of hooks into your npm thing, and so the way you actually do a recompile is to do an npm install. So obviously, if you have a lot of modules, and they'll be cached, so it won't actually be doing that, but it'll actually trigger a build. And so for this project, it's going to build. Well, I'll just show you what happens when I do this. This is going to run the Node JIP. This is now running the build, and it's completed. So this is a bunch of warnings. These warnings I should actually fix, but I haven't. to give you a real representation of how long the compilation takes, I'm going to delete the build folder, because like it doesn't rebuild things it knows it doesn't need to rebuild. That's one of the, like, I mean, C and C++, they're not really known for their like lightning fast build times, but the one thing they do have going for them is that if you make a build of a file or a compilation unit that you have, a translation unit, and you haven't changed it, it won't build it again. So that's kind of one of the nice things. But in this case, this is how long it would actually take to build. So it's running, building, it's done. So in this case, for this relatively small library, I mean, like, what my add-on is doing is basically binding to this other pre-existing library. That pre-existing library takes a little bit longer to build. I have the source here, and so you need to factor in that when you would install this, like if you were installing the extension, it would first need to build that library first, and then it needs to build your code. And actually, I haven't gotten into the whole release flow stuff of a Node add-on extension, but one of the things you can actually do is kind of make pre-builds for different platforms. But a lot of the time, you know that like your user probably will have to build for their platform, especially if you're on something that's like, you know, just has an environment that changes relatively often, like Mac OS, something like that. But yeah, it's pretty cool that the npm install does it for you indeed. It's a straightforward way of doing it, and I think there are commands that you can pass to, like, there is like a node jip binary and there's like a node add-on binary, and I think you can initialize some, you can throw some commands at those things themselves, but npm install is basically the easiest way to do a rebuild. Yeah, so it's pretty straightforward, I would say. I'm still learning about the whole cycle of how to really make sure that this is a nice robust system, and definitely like building this kind of stuff on different people's systems is like, you know, I think that's where you can really end up like pulling your hair out, because everyone has a different environment and people have different libraries installed on their Linux systems and that kind of stuff. So if things start clashing in that way, like, you can run into some pain. But yeah, from my side, it hasn't been that bad so far. All right, I think if there aren't any more questions or anything like that, then I think I'm gonna end the stream here. So I want to say, yeah, thanks to everyone for joining this evening. I know that we didn't really like write any code in this stream, and it's mostly been like a catch-up session. But I think the next stream where we do some stuff with this, and I don't know if the next stream will be working on this or working on something else, but in any case, the next stream where we work on this stuff, we're definitely going to be writing some actual code, and I hope that you'll enjoy and won't mind if we write some C++ code in that case, or if we write some C. We're also going to write some TypeScript. What I really want to do is just blend all of those things together. One of the things that's super cool with this project in particular is that it spans 4 programming languages. We've got JavaScript, of course. We've got TypeScript, which I think is like a necessity for something like this as well. We've got C++, which we need for the Node add-ons, and then we have C, which is the language we actually write and bind to for the FTDI library. So, I mean, there's not that many other projects out there where we need to span that many different programming languages. I think it's really cool. So I hope you'll enjoy that too, and I hope you've learned something. Yeah, and I think I'll see you next time.